Thank you so much for inviting me to be one of the keynote speakers here at SIGSPATIal 2020. I'm really excited to be here and, frankly, a little bit nervous. This is one of the premier venues for talking about geographic information systems, and a lot of my career has been focused on this idea of exploring spatial phenomenon with geovisual analytics. Currently, I serve as the director for one of the 10 Department of Homeland Security centers around the United States. I'm the director of the Center for Accelerating Operational Efficiency. We're a consortium of universities where we are led out of Arizona State University. And while we have a little bit of a strange name, I'm hoping that our mission that you hear will resonate with some of the ideas in the SIG spatial community, where our goal is to develop and apply advanced analytical tools to optimize efficiency in homeland security operations. We are really sort of the data analytics research branch here in the Centers of Excellence Network. Our research teams are on data analytics, operations research, economic analysis, and homeland security risk science. And hopefully, those sorts of themes are resonating a little bit with the community. The goal of this conference has always been to bring together practitioners and developers of geographic information systems to start thinking about how we might work together in this interdisciplinary space. And a lot of the decision making that needs to be done has an underlying spatial component. And our expected outcomes are to build real-time decision making tools, build applications of analytic tools to help DHS operational components and other security practitioners achieve improvements in operational efficiency. We have projects such as how can we improve queuing at airports, or how can we look at human AI teaming for decision making. But a lot of my career got started as a graduate student working for the Department of Homeland Security under what's now been the Sunset Center for Visual Analytics and Data Analysis, CVADA. And CVADA had two branches. One was the Vaccine Center at Purdue University, where I was a graduate student, and the other was the Cicada Center at Rutgers. And in vaccine, my research focused a lot on building geographic decision support systems. So we worked on creating tools and techniques for analyzing criminal incident reports. We built out the Visual Analytics Law Enforcement Toolkit under the direction of David Ebert for doing crime futures analysis and resource allocation and planning. So taking kernel density estimation, combining this with seasonal trend decomposition using low-S smoothing to create these predictive models to show where crimes might occur tomorrow, to look at how we could create patrol routes and how we could convey this information to police officers. We applied these same techniques for looking at search and rescue cases for the Coast Guard. In the Great Lakes area, a lot of the Coast Guard stations are being manned by volunteers. As these volunteers are getting older and retiring, we weren't seeing new volunteers coming back to the workforce. So now stations either need to be funded or closed. And so we were asked to build some sort of analytic tool to show the distribution of cases and allow them to play what-if scenarios with decision tools to say, if I close this station, how does this impact my response time to estimated search and rescue cases? And all of these geographic decision support systems tried to look at how we could put the user in the loop to explore different futures, compare portfolios, and these sorts of things. And back in 2009, one of the interesting topics that came up was the potential for an influenza outbreak, especially with H1N1. And at the time, we built what was called the Pandemic Influenza Modeling and Visualization Tool. Colloquially, we called it PanVis. And this was designed primarily for emergency response planning tabletop exercises where users could adjust different sorts of control metrics. So we had a simple SIR model that we used, and we looked at saying, well, what would happen if we add some sort of school closure to the model? Or what if we had a strategic national stockpile and could deliver antivirals? How would this slow the spread? And we worked with partners across the US to do tabletop exercises to help for training, sharing maps like showing what would happen to the pandemic spread on day 37 with no decision measures implemented compared to what if we implemented all decision measures. And this is, looking back, relatively naive model in terms of this only looks at things like hospitalizations, death rates, illness vectors. What we see now in our current situation is the problem becomes more complicated. We wind up with politicalization of science. We see um, challenges in the supply chain for delivery. We see large-scale economic impact. And these are some of the problems that our new Center for Accelerated Operational Efficiency has been taking on during COVID-19. We've been funding studies looking at things like what COVID-19 is doing to the US economy, trying to break this down by sector. All of these different sectors have different policy levers, different things that might need to be done. So here, our partners at Victoria University are funded to build computable general equilibrium models that are used to estimate how an economy might react to changes in external facts, such as a pandemic. So they use data from the Bureau for Economic Analysis, looking at how GDP might change, looking at different sectors, and you can see the in our table here, these are the changes in sector by quarter, so the quarter of 2020, first quarter, second quarter, third quarter. And I thought what was an interesting quote that I heard in the paper was that the US isn't just one COVID-19 outbreak, it's 50. We have all the different states handling things slightly differently. We have different policies, political boundaries, geographic constraints, population constraints, economic constraints, and all of these are really challenging in sort of dealing with these problems. And so we're sort of looking at this cascade of effects and different things that need to be modeled, but all these things need to be considered at once. Other ongoing projects, we've been looking at how the supply chain's been disrupted. So here we've been working with funding partners at Rutgers University, the old Cicada Center. Here in the early parts of COVID-19, we saw the sudden shift in demand locations and panic buying led to challenges in the food supply chain. This was exacerbated by threats to the labor supply as workers became sick, as different plants shut down, as people chose not to return to their jobs for fear of getting ill. We saw that companies couldn't provide enough medical equipment and personal protective equipment. We had shortages worldwide, which further exacerbated some of these issues. And then these shortages and chaos also provide opportunities for criminal activities. And so Cicada worked to put together a supply chain workshop with the Department of Homeland Security, trying to look at lessons learned to better prepare for future disasters, to look at issues on how we might do better vaccine production and distribution, or even thinking about what tools and technologies are needed to help understand these sorts of complex problems. And while I've been focusing these last chunk of slides on issues of COVID-19, this is just one example of what we can term as a wicked problem. And wicked problems are complex and interconnected, and we have limited resources to throw at these things. Another example of wicked problem is climate change. This has been seen as a significant challenge for the United States and the world. You can read about this in the Quadrennial Defense Review from 2014. But changes in global dynamics, including growth, urbanization, exacerbate water scarcity, lead to sharp increases in food costs. We get resource competition. These place additional burdens on economies, societies, and governance. And so we're living in this space of hugely interconnected systems. And I think it's important for the SIGSPATIAL community to think about where we might be able to make the best impact. So there's 10 properties that define wicked problems, at least from the dilemmas in a general theory of planning and revisited in strategy as a wicked problem. And while I know that we've heard these phrases about wicked problems over and over, I think it's useful to take a moment for us to revisit these definitions, as this is primarily talked about in management science and policy. So one of the key things is there's no definitive formulation of a wicked problem. It's not always possible to write a well-defined definition of a wicked problem. If we're talking about climate change, the classical systems approaches of the military and space program is based on the assumption that a planning project can be organized into distinct phases. So every textbook of systems engineering starts with an enumeration of these phases: understand the problems, gather information, analyze information, synthesize information, and then wait for a creative leap or work out a solution. But for wicked problems, that scheme becomes more complicated. We can't understand the problem without knowing about its context, and we may not necessarily be able to meaningfully search for information without the orientation of a solution concept. So we have all these interconnected things that require domain expertise and discussion between these different experts. And there's not necessarily a stopping rule. We can't tell when we've reached a solution for a wicked problem. So we can continue searching over and over. And of course, wicked problems aren't necessarily true or false. Maybe they're more good and bad. There's a lot of parties that are equally equipped and interested and entitled to judge the different solutions that are posed for these wicked problems. Um, but we don't necessarily have the power to set formal decision rules to determine correctness. There's no immediate and no ultimate test of a solution to wicked problems. The full consequences of our decisions may not be able to be appraised until the wave of repercussions have completely run out. And we may not have any way of tracking all of these waves, looking at all the different lives that are affected ahead of time, given that we have a limited time span to sometimes make these decisions. And then every solution to a wicked problem is often a one-shot operation. There's not necessarily an opportunity to learn by trial and error. If we enact some big policy decision, yes, we see trial and error, but we can't necessarily easily roll back these policy decisions. Every attempt counts significantly. And so it's a matter of judgment which solution should be pursued and implemented. And these wicked problems don't have an exhaustively desirable set of potential solutions. There's not necessarily a well-described set of permissible operations that can be incorporated. So in these fields of ill-defined problems and ill-defined solutions, the set of feasible plans of action rely on realistic judgment and the capability to appraise exotic ideas and on the amount of trust and credibility between the planner and the clientele to lead to these conclusions and say, okay, let's try that. That seems to be a reasonable path forward for all the stakeholders involved. And every wicked problem is very unique. I talked about COVID-19 to give sort of a context of a wicked problem, showing how this inter cascade of supply chain to pandemic to economy to all these broader things that have different policy choices are very interconnected. Climate change, same sort of problem. And an ordinary problem belongs to a class of similar problems that are all solved the same way. A wicked problem often doesn't have precedent. It's not that we haven't had pandemics before, but the conglomeration of events that have occurred at this point in time, our past experience maybe doesn't always help us address this. And every wicked problem can be considered to be a symptom of another problem. So an ordinary problem is sort of self-contained, a wicked problem is entwined with other problems. And so despite seeing similarities among wicked problems, we may not be able to be certain that the particularities of a problem don't override its commonality with other problems. So just because I was able to deal with this one way for a certain set of data may not allow me for another. And the existence of a discrepancy in representing a wicked problem can be explained in a whole lot of different ways. For example, we can think about crime in the streets. This can be explained by not enough police, by too many criminals, by inadequate laws, by too many police, by cultural deprivation, by deficient opportunities, by too many guns, by too few guns. And each of these offers a different direction for attacking crime on the streets. Which one is right? There's not a rule or procedure for us to determine the correct explanation or combination of these. This is why we wind up with so many different studies trying to carve off different pieces. And we want to think about how we might be able to combine and look and gain this sort of collective intelligence. And studies of causality could benefit this. And we've been making lots of progress in that space in computer science, trying to think about how we can look at causal impacts and effects in the era of machine learning. But here the issue really is that the planner doesn't have a right to be wrong. Problem solvers dealing with wicked issues are held liable for the consequences of any action they take. When we make a policy decision, we have long-term impacts, and they have a large impact. And those impacts, if they're negative, may be really hard to justify because it's difficult to look far out into the future sometimes. And so here I just want to go through these 10 properties of wicked problems to set the stage. And I worry a little bit because as this defined, maybe it feels a little bit like I've said, well, there's no way to make progress. But if we take another look at these sorts of items, I highlighted a few where there's no definitive problem. There's no immediate or no ultimate test. Every solution's a one-shot. Every problem is unique. The planner has no right to be wrong. And so I think what resonated with me in thinking about this was really the planner has no right to be wrong. And the SIG spatial community has focused a lot on the need for better decision and planning tools and processes, especially in the geographic context. Spatial decision support systems tackle a lot of different problems, and we have a lot of different contexts, and these need a lot of different computer science sorts of support, from improving querying process speed, combining models, and working together for creating new plans and techniques with our stakeholders. So I think it's exciting for us to think about what can the SIG spatial community do in this space of wicked problems. We're being confronted with this sort of cascading effects with lots and lots of spatial data at our fingertips now. What can we do, and how can we enable a broader view of geographic information systems? And really right now, it's not just models and data, but we also need to enable um, our stakeholders with ways to explore future scenarios. How can we help them adapt and anticipate? And of course, there's the famous quote by George Box that said, all models are wrong, but some are useful. So as we're building out these new models, as we're gathering new data, how can we help make all of these things useful for our partners, for our stakeholders that may not necessarily have a strong computational background? Because models are increasingly being used to represent, understand, and communicate complex systems. Efforts to enhance the contributions of science, thinking about things like sustainability, have been met with mixed successes. So if we're thinking about climate change, the integration of environmental science and policy has been hampered by unrealistic expectations about the ability of science to inform policy decisions. It's hard. Differences in scientific and political understanding and can limit our viewpoint, can limit achieving scientific consensus. And we have different timescales for scientific studies, political processes, social cultural differences between science and policymakers. And so these attempts to link science and modeling with different decision making have sort of yielded mixed results. So it's not just about building a better, more accurate model. I also want the SIG spatial community to think about the decision-making process too. And this is where I think visualization comes in to help us elucidate some of these challenges and some of the problems we're seeing in data. And so I want us to start thinking about how we can anticipate, visualize, and respond to wicked problems in the context of governmental policies. And this is where we have to break out of our shell and reach out to our policy partners in the social sciences, in all sorts of different communities to start thinking about how we can handle these really complex interdisciplinary problems. And there was a nice paper that came out of ASU in 2010 talking about how decision tools, in order to be effective in linking scientific knowledge to decision making, we need three things: saliency, credibility, and legitimacy. So saliency means the relevance of the model to the decision maker's needs. Credibility is how valid or reliable are the technical accuracy of the knowledge and analysis presented in the model, and legitimacy focuses on the perceptions that the knowledge and information is respectful of stakeholders' diverse values and beliefs. So we want to think about how we can handle building tools and methods that are salient, credible, and legitimate to our end users. And I think this space is really prime for this community, where we're looking at a need for an integrated approach where we need scalable analytics, data visualization, and advanced computing and flexible software, where we can take large-scale models, large-scale data, integrate these things together, and have some sort of visualization tool for exploratory data analysis, exploratory decision making, looking at trade-offs and pros and cons of the potential decisions that people might put into place, looking at different policy trade-offs. and then talking to different stakeholders to get and gauge their reaction on these sorts of works. And like I said, this requires scalable analytics. We need applicable analytical tools demonstrated in the context of diverse data sets. And this community has worked on a lot of these things. We've had problems in sustainability, disaster recovery and emergency response, economics, finance, personalized health. There's been tons of work here on computing and flexible software. So thinking about traditional HPC work, MapReduce, cloud computing, traditional and NoSQL databases. And we're seeing lots of exciting work on how we can scale up some of these geographic information systems on the back end. Things like GeoSpark are extremely exciting. Things like PySal, making spatial analysis more open to the public. All sorts of exciting tools are coming out of the community. And so thinking about this intersection of saliency, credibility, and legitimacy, we can think about this intersection of visualization, visual analytics, modeling, simulation, and stakeholder engagement, and maybe start thinking about what would an immersive collaborative engagement platform of the future look like, especially now if our decision makers are all working remotely. How do we handle this? In modeling and simulation, we may have discrete simulations, agent-based models, multi-resolution models. In visual analytics, we may want to reduce the data because we can't show everything. We're going to have to fuse different data sources together, and we want to tell a story about what's going to happen in the future and allow people to explore these different narratives. And all of these need to be framed correctly for the stakeholder and enable and encourage collaborative decision making so that people can look at trade-offs, benefits, and come to some sort of agreement and decision about policy. And so let me just talk about a couple things that have been going on with this. And so with stakeholder engagement, we want to think about how do social groups in the knowledge action system differ in terms of, for a talk on climate change, environmental concern, but risk perceptions and policy preferences. And there has been some work in this. Again, another paper at ASU was looking at simulations of water futures, and they had 3 different stakeholder groups they brought together to try to elicit how their differences of opinions were. So they had the broad public, policy professionals, and academic scholars that they surveyed. And they gave them some policy choices and asked them how strongly did they oppose or support. And a 1 was they oppose strongly, and a 10 was they strongly support. So for example, in asking these 3 different communities about increasing the price of water, we see a significant and large difference. The general public does not support increasing the price of water, where the academic community does. However, if we think about educating the public about water use, this has broad scale agreement. And even in investing in new technologies, while there were significant differences at the 0.05 levels, we do get closer to some level of agreement, as well as things like improving management. And so the reason I wanted to talk about this slide in this study was just to show we do have these broad scale disagreements. We need to think about how to encourage the stakeholder engagement to think about trends, trade-offs, changes within our different systems. And so along with stakeholder engagement, a big portion of modeling futures is building models. Another project at ASU that my group has been involved in has worked with the Decision Center for Desert City, working with Dave White. And Dave White's team built this wonderful tool called WaterSim to allow scientists and decision makers and educators and the public a way to explore alternative scenarios for the future of water. And these are one type of boundary object that's become popular for linking environmental science and policy together. But how do we link these two more complex systems? And you're seeing calls for this from the National Science Foundation. We have the innovations at the nexus of food, energy, and water systems, trying to think about how do we put together these really complex systems. And so this is just sort of giving you an idea of the simplicity of the WaterSim interface, where people can explore different policy choices. And we try to create some pictures of sustainability indices to give some overarching feeling about how these policy choices will impact things like groundwater usage or the environment or agriculture. And we even tried deploying this in museums around the country in partnership with the Smithsonian to try to elicit and understand how education about policy choices through visualizations might help the broader public. And so along with modeling, there's been a concentrated effort in novel data collection sources too. All of these models require different sorts of data sources, and I think there's some fascinating work going on at Arizona State University led by my colleague Ariana Middle. And Ariana Middle and I have been working on what she's coined as urban climate informatics. So right now, we've got urban form, composition, design, and green infrastructure impact urban climate. So we have the formation of urban heat islands, which are really critical in places like Phoenix, Arizona. And local and microclimate, you have air temperature, wind speed, surface temperatures that are at a very fine scale level that can impact the energy use of buildings, the pedestrian heat stress. But currently, we sort of measure these at a more macro scale, at a different sort of sampling rate. We lack fine scale data to describe the form and function of cities. So if we're trying to think about how we might build more comprehensive models, can we think about how urban form and function can be described from a human-centered perspective? And so um, Ariana had this great idea about, well, why don't we try scaling up using big data? And so her and I worked together to take Google Earth data, Google Street View data, to capture information about the urban environment. A Google Earth virtual camera tour gives us 5 meters spatial resolution. Google Street View data, we can create synthetic fisheye photos, get views in 5 directions, and do simple things like capture how much sky is in an area. These issues of doing sky view factors and analysis are really critical for forming some of these local models. Sky view factor is a fraction of the visible sky viewed from the ground up. And these are commonly used by urban climatologists to quantify the openness of an urban site. And this is strongly related to urban heating. So if we have low amounts of sky view factor, we get reduced long wave radiation loss at night and reduced short wave radiation gain during the day. And Dr. Medell has this really cool sensor robot called Marty that goes around and captures these local climate values. And then we can use that to validate and see if what we're being able to extract from Google Street View matches sort of reality for these local climate models. And she's applied this to all sorts of places, making high resolution sky view factor maps for Phoenix, where the darker red means low sky view factor, so in these sort of urban canyons, and blue, you're sort of seeing the suburban sprawl with low buildings, 1 or 2 story residential houses. And so for each city across the world, we can make these different sorts of maps and characterize these and start building models about local urban microclimates. We can use thermal comfort equations to calculate human radiation balance and mean radiation temperature. So how hot are you going to feel at a very particular place in the city might change based on urban factors. And mean radiant temperature is just a measure of the average temperature of surfaces that surround a person. It's the sum of all short and long wave radiations. There's tools like Rayman that can calculate MRT using these equations we get from these fisheye photos. And then we can start thinking about other applications we might do if we have these models. So for example, what if I want to walk across campus? I can try to make a more heat efficient route. So if I were to say, well, I want to walk across campus and take the coolest path possible, it's a time constraint, right? So you may say, well, I'm willing to spend an extra 5 seconds outside if I get more shade. But by taking all of these photos from Google Earth and from Google Street View, we can get these thermal comfort factors, and we can show that different routes at different times of day through the campus will be more comfortable and more shady. But what's interesting about these different urban factors is we can also then start working with city planners and policymakers to take other data sources and combine together. So imagine if I know all the class schedules for students at ASU. I can start computing trajectories, plot these on a map. I know the time of day, so I can start sort of computing sun exposure per student and get this idea of where we might want to invest in more urban infrastructure to accommodate for this. Imagine doing this for the city and at the high level planning region. And so again, while this may not be such a wicked problem, this is just one way where we can get more data for some of these models. And it opens up the door for tons of interesting applications that can all go together for policy and decision making. So you can do things like walkability assessment. If I have all these Google Street View imagery, I can create a walking score for a neighborhood. How much pedestrian crosswalks are there? What's the um, curb cut? That's the distance from the road to the sidewalk. I can look at what's the shade on the road, and we can use this for targeting tree planting or shade structure. And you've seen Google apply some of these ideas already. Google had the solar sunroof project for taking satellite imagery of your house and estimating how much solar energy you could get based on the orientation of your house and sunlight. The government in Greece was seeing a strange set of tax returns by people in a very wealthy neighborhood. So they started taking satellite imagery of the wealthy neighborhood to identify people whose houses had pools and to then compare these housing locations to income taxes and trying to see if perhaps there was income fraud in this. We can even think about taking these things for building bike paths or providing heat warning systems for marathon events. And so right now we're living in this really exciting time of data, modeling, simulation, visualization. And putting all of these together, we can build these visual analytics frameworks. And visual analytics has always focused on this idea of converting data into insight. So we're trying to combine advanced analytical algorithms combined with interactive visual interface to allow the user to explore these and combine that domain expert knowledge with these advanced analytics and data exploration. And I just wanted to talk about a couple of interesting problems we've been working at in our lab that sort of require these combinations of multiple stakeholders. So one of our recent projects has been on visual analytics for conservation planning. So we want to take all these different data land attributes to try to help people determine what land portfolio they should purchase. You have a limited number of funds. Let's say you're a nonprofit organization that can buy land. How do you determine what's best? And you have different competing ideas on what's going to be best for the environment. Some people have a very particular species of animal in mind that they want to protect. Some people want to look at broader landscape for animal transition corridors. And so we have all sorts of analytical tasks for investigating land attributes, filtering parcels that people can buy, and we design map views and parallel coordinates for allowing them to compare and trade off different portfolios. But I think some of the challenges here that the SIGSPATIAL community could have helped with have really been on the data management side. These data are captured at different scales, different resolutions, aggregation, quick aggregation to scale up and to sort of get these all within the same operational framework at the correct geographic level is difficult and time consuming and sometimes hard to explain to end users. Another exciting project that we had working on was with Tony Grubisek's group. He's now at the University of Texas in Austin and thinking about visual analytics systems for oil spill response and recovery. So if a pipe bursts in the Gulf of Mexico, there's lots of simulation models that'll now show where the oil might beach. And now we can start thinking about how communities might be impacted. So we can start thinking about economic impact and also environmental impact. But the trick is we still have limited funding, limited resources for cleaning this up. So here we wanted to build a tool that could combine these sort of high performance computing models, show the flow of the oil particles across time, and compare different sorts of cleanup portfolios. How much money, how many boats, where are the boats stationed, what's the impact going to be to different environments, environmental regions of the coast, to different economic communities. And this becomes really a critical problem. Different stakeholders live in different communities and they want their community to be protected, and trying to explain the risks and trade-offs between these and the cost benefits and even the limitations of what resources are available are extremely critical. And so I think combining this idea of saliency, credibility, and legitimacy, thinking about visual analytics, modeling and simulation, and stakeholder engagement is a really, really exciting domain area for us to play in. And so I wanted to sort of think about what do I see as some of the fun and still ongoing challenges that maybe the SIGSPATIAL community can tackle. So let's take it back to COVID-19 again. One big impact of COVID-19 is we're remote. Here you're listening to my talk. I spent time recording this, uploading this, and this access to broadband internet has created a lot of disparities in terms of your ability to work, get educated, and we're seeing this take place in drastic ways. And there's people that really want to study broadband connectivity in the US and broadband provisions in the United States. But the problem is spatial temporal data collection is still hard. I showed this in the urban informatics stuff. There we were collecting Google Street View imagery, large scale images, really high resolution that then needed computer vision models. But even simpler government collected data, like the broadband provisions, are a pain to work with. The fixed broadband development data from the FCC has 3 unique time spans, and each time span has its own problem in connecting to the next one. So we have 2008 to 2010, where this was in the 2000 census geography at the tract level. We know the number of holding companies. So then 2011 to 2013, we have the 2010 census geography. So we need to do spatial alignment, so converting the 2000 tracts to the 2010. We know how to do this. There's crosswalk files that allow you to convert these numbers. The problem is you have suppressed data, because if you have between 0 and 3 holding companies in a tract, you just write down 1 and you say that's suppressed. So as you convert and move across time, you may suddenly jump from 1 holding company to 7. And it looks like you had a huge jump in the number of broadband providers, but really it may have just been 3 new companies moved in. And then in 2014 to 2018, now the new data just came out, we had detailed information on what holding companies are within each tract. But now we don't have the count. So now you need to, in order to line up those 2 previous time series, you need to count the number of unique holding companies and line those up. And none of this is hard. All of this can be done in Python scripts. But if you just go to the website and grab this data, it's challenging for people that may want to do these economic analyses. You have to invest a lot of time in integrating these and cleaning these. And so, we have projects on how we can integrate this sort of thing and align those and look at different errors. And while you say, well, this is a relatively solved problem, I would argue that spatial data wrangling is still extremely challenging, because you have these different levels of aggregation. You have these different levels of time scales. Imagine you want to take broadband provisions that are giving counts of providers yearly, to educational outcomes that may be only collected every 4 years, to economic outcomes that are collected quarterly. How do we align these to allow for meaningful analyses? And how do we make sure that people are not applying poor statistical techniques? And like I said, it's hard. In the urban climate informatics, microscale data collection isn't continuous. If I take a picture of Phoenix, in 2016, it may not look the same. So remember my example of showing my path across campus here on the map? Well, you see that diagonal part here? That's a parking lot that is now a high-rise and completely changes the shade structure of this entire block. So walking from my office to the far point on campus has a completely different sort of pathway. So urban landscapes can change really quickly. So how do we start working with different groups to make some of these data sets more accessible to allow for these analyses? And part of the reason why I talk about data collection being hard is your local government and local policymakers don't have a lot of money to invest in these sorts of tools. And so that's where a lot of manual data creation labeling in geographic data sets is still really common, and is funded by things like nonprofit organizations or governmental agencies that may eventually run out of funding. One example is the Global Terrorism Database. This was funded by the START Center of Excellence, again, one of the 10 Department of Homeland Security Centers of Excellence. These centers are slotted to run for 10 years. At the end of the 10 years, they're sunset, the funding goes away. And so this wonderful data set they've been collecting for 10 years suddenly doesn't have funding for people to keep downloading these open source articles, grab information on terrorist events around the world, update the database, let alone pay for storage and all these sorts of things. So how do we start thinking about making this more robust? And do we need all this manual labeling now that we've become quite good at techniques for NLP and AI, but still linking spatial locations and names to events is hard. You know, in your Twitter profile, you may say, I live on Earth, but there isn't Earth, Texas. One example of this sort of continual data collection is the armed conflict and location event data. This is run by a nonprofit that collects real-time data on locations, dates, actors, and it even gives confidence to the different articles that are being collected. And we've seen progress in the SIG spatial community for collecting all of these news source articles and processing these. Hanan Samet has his wonderful newsroom sort of work. But how do we take that human intelligence across these different countries to tell us how trustworthy a news source is? How do we get all of these translated? Where do we save this to allow for this large scale longitudinal study? And how do we connect those armed conflicts to global terrorism to economic policies that are captured at vastly different scales and integrate all of these things together? I've been hearing a lot about explainable AI, but I think we also need explainable maps, explainable geointelligence. When we get people looking at a spatial decision support system and a geographic information system, they love it. They love talking about maps, right? Because you can relate this to your personal experience. You lived there. So here on the left, I'm showing you a map of sort of the Phoenix metro area. And that bar chart is showing the top 100 locations of zip codes by growth of COVID-19. This is a map on September 1st, 2020. And without context, you're like, oh, wow, zip code 85281 had a big growth. But the obvious question there is why? And with just a little bit of the right context, you can start putting together the answer to some of these whys. Zip code 85281 is Arizona State University. School opened 2 weeks prior to September 1st, and you started seeing a large spike in cases about 2 weeks after. Another example of thinking about how we can explain maps. On the right, this is a picture of sort of the Seattle region, and the darker the color the red, the higher the projected of future housing values are in those places. So this is done with a geographic weighted regression model. But the question begs for more context about what's going on in these high value places. And if we plot things like the University of Washington or Bill Gates' house or Amazon, we can start rationalizing about these sorts of things. And so how do we help explain more about what's going on in a geospatial context? Because with geospatial systems, people are often wondering about causality, and they often are relating these to personal experiences about geography that may or may not be wrong. So how do we help curate and tell a full story about these things? And how can we bring all of this together? We've worked on trying to build tools that maybe can help people annotate different timelines that are related to space and news articles and things. So building causal models and letting people pick out different news sources that relate to them. So here looking at food shortages and temperature extremes and hunger, annotating those articles on a timeline, pulling out different actors for people that were rioting perhaps, or police forces, annotating those so you can help build out your mental model of how your geography and timeline and events might have some sort of cause and effect to help tell a story. And building these tools to capture that analytic provenance along with the data and being able to represent that back to the end users, I think is really critical and exciting. And then we're hearing a lot of this talk about explainable AI, and we talk about how we can open up these black box models to explain this and make the model more salient. But the question becomes, should we open the black box? Do we need to? How much should the human be involved in opening this black box? And I don't know, I was playing with this idea of, we have this concept of auto ML, where you just take your data and machine learning algorithms can automatically decide what statistical models to run, what parameters to set, all these sorts of things. But what about auto GeoInt? You know, PySal and other libraries are making it a lot easier to do spatial analysis, but the trade-off is anybody that can run Python can just take their data and say, let me do a geographic weighted regression. And they may not have any business applying the different parameters, bandwidths, and all these things that they applied. Just because I can run a function doesn't mean that I should. So where is our work towards creating these sort of auto geoanalyses to give people and novices some sort of insight and also create trust that, yes, this has been validated and we know that we're picking the right models and constraints for this. And as I talk about all these models, I talked about very specific subsets of different problems that we've been working on, but we really need to think about how we can better enable a flexible combination of models. How can we help planners that are going to be making these policy decisions? How can we help modelers put these things together? Here's an example of our work for the Nexus of Food, Energy, and Water Systems in Maricopa County. And this is just a very simplified network view of looking at agriculture regions, power supply, and water supplies. And each of these may have some sort of underlying model coupled with economy, trying to think about how these things move, work together, fit together. And now you have models that are operating at different spatial and temporal resolutions. And so it's critical for thinking about how we can improve this model flexibility and combinations. And with this, these complex systems of problems, given that they can be thought of networks, what are our new techniques that need to be developed to represent these complex systems networks to stakeholders? There's been tons of work in knowledge graphs and representations, and if we're combining these different data sources together, can we connect these knowledge graphs automatically in the background to provide more feedback? Can these knowledge graphs then be used to augment and easily link new data sources as we pull these together to link new models? And how can we identify and visualize potential cascading effects of policy decisions in these complex models? So hopefully this has led to some interesting food for thought. We all live here on Earth. No decisions are easy, but I really want to encourage us to break out of disciplinary silos and leverage all of our different research that we have going on, all our different research capabilities to address these sorts of wicked problems. I can't wait to sort of see how we're going to start building this computational infrastructure. So it's important here to say all this work is based on a lot of funding from the Department of Homeland Security and National Science Foundation. Please, all the views and conclusions are that of the author and should not be interpreted as representing official policies. And I'd be remiss not to thank all of my wonderful students that helped make this possible. Here's our last lab dinner before COVID-19 at the Thai restaurant. I can't wait until we can get back and all of my students and I can enjoy a nice visit to a conference such as SIGSPATIal, a nice meal together. If you have any questions about our work, please visit our website, vader.lab.asu.edu. And I'm happy to take any questions about Wicked Problems, our Center of Excellence, or anything. Thank you so much for listening. It was really my pleasure to give this talk. Thank you.